Hi students, for this first video for online lecture 18, we are now going to introduce many of the definitions for chapter 10 and the beginning of thermodynamics. So let us talk about the types of energy that you commonly run into. The first one that we want to talk about is just the overall definition of energy. It is the capacity to do work. Work being directed energy. We will show you how to calculate work here over the next couple of lectures. The first type of energy that we want to talk about is radiant energy. This is the one that comes from the sun and is Earth's primary energy source. So as you can see here, I am tying famous songs to the types of energies. So more than likely, you're probably singing Here Comes the Sun by the Beatles right about now. An important one is thermal energy. This is energy associated with random motion of atoms and molecules. So the important part about this is that the thermal energy that we see in our combustion reactions is very much going to be a part of our vernacular. We can also look at chemical energy, which is the energy stored within the bonds of chemical substances. So as you can see why these two are boxed, historically we are going to break chemical bonds in order to release chemical energy on the hopes of it becoming thermal energy. This transfer of energy is going to be necessary for us and determining our calculations this chapter. Nuclear energy is the energy stored within a collection of neutrons and protons in the atom, and when harnessed, gives off a great amount of energy. Hopefully you will get to that chapter when you are in your chemistry 2 in the later course. And finally, potential energy is the energy available by virtue of an object's position. Potential energy is an important deal when dealing with physics because we like to see the energy that is released from the potential side becoming kinetic energy later as it falls from elevation. The important part is not just only the types of energy, but what we can do with it. So, what we like to normally talk about is the conservation of energy. That energy is convertible from one form to another. We typically call this the law of conservation of energy. Energy cannot be destroyed or created, but we are going to transfer it from one media to another in one form of another. So historically, what we are going to look at is that change of our chemical energy to kinetic energy, or in many cases, what we're going to look at as our radiant energy becoming useful kinetic energy. But as you've learned, what we are going to do is now change the law of the conservation of energy to its official and appropriate name. That is the first law of thermodynamics. In this course, you are going to learn solely about the first law, and as you get to your thermodynamics course in Chem 2, you will pick up the other two laws that specifically talk about entropy. So now let's talk about what thermochemistry is. This is the study of heat changes in chemical reactions. The system is the specific part of the universe that we are interested in studying. You get to define what the system is, or when you are working on your online homework, they will tell you what the system is. This means that we are going to isolate out a small part of the universe to focus our experimental study on. The rest of that world is going to be known as the surroundings. So let's take a look at a few of our systems. Here is an open system. In an open system, we are allowed to have anything exchange, mass and energy. So just imagine that you are cooking spaghetti using a hot pot of water. If we do not put a lid on our pot, not only are we going to let energy release, but we are going to lose water in the form of water vapor, and you can see that normally by the condensation that ends up on your stovetop or on the front of your microwave if you have one. So in this case, we need to find a way to limit the loss of our mass. So what we can do is now go to what is called a closed system. So as you see here with my bottle, I've put a stopper on it, or if I'm using my hot pot of water, I would put a lid. And now all we are going to do is transfer and exchange energy. There's no mass loss. So that's one of the important parts of going and covering your boiling water, is because the water is going to try and escape. It will hit the glass, possibly recondense, and fall back into the water in the pot to be boiled again. At that point, you're not losing any mass of water. The last type of system we want to discuss is typically what we call an isolated system. This means that nothing leaves or enters. A fantastic example of an isolated system is a Yeti cup or a thermos. Remember, if you were to put a cold beverage in a thermos or in a Yeti, you would be able to keep it cold for a long time. When I was growing up, my mother would heat up soup, put it in a thermos, and by lunchtime it was still warm. Why is that the case? Because the energy has nowhere to escape, so it continually keeps that heat in the soup so that 3, 4, 5 hours later it is still ready to eat. When dealing with our Yeti cup, the reason it is a good insulator is that it does not allow energy in to warm up your beverage. So if you put ice and water or ice and Dr. Pepper into your Yeti, the energy is not allowed in to melt that ice and heat up your liquid. So when we are dealing with that, the cold or lack of energy is being contained inside of that cup. So now let's talk about what we know as heat and temperature. Heat is the transfer of thermal energy between two bodies that are at different temperatures. Temperature is the measure of thermal energy. These are not equivalent. Heat transfers from species with more energy, the higher temperature, to the compound at lower energy or lower temperature. Eventually, they will be at the same temperature, which we will call thermal equilibrium. So let's talk about the three major types of energy transfer. The first one is conduction. This is where energy is transferred by direct contact. So as you can see in my figure here, we have a hot pan, and I am going to touch that pan with my bare hand. Before I touch it, my hand is at a lower temperature than the pan. The minute I touch it, that pan is able to transfer energy to my hand very rapidly, and that is what causes the pain. That energy is going into your cells, and depending on how much energy that is, you might get destruction of the cells, and that is how you get blisters and burns. Convection is the second way that we want to talk about energy transfer, and that is energy is transferred by the mass motion of molecules. So as you can see here, we have a pot of coffee that we are heating through, or in a lot of ways of how we go and form thunderstorms. Notice that you see that there are hot air molecules that contain a lot of moisture, and as they rise, because it gets further away from the surface and into higher elevations, they cool down, and that is what causes our storm clouds and our precipitation. The last type is radiation. This is energy transferred by electromagnetic radiation, which we've seen in a previous chapter. So as you're sitting by a campfire, or you're wanting to look at a light source and energy is given off in the form of heat, this is the type of radiation that you would expect. The important part about this is that we need to have quantifiable numbers in order for us to discuss heat and temperature. We will talk about heat using the units of joules and kilojoules. That is the SI standard unit. In temperature, we are talking about temperature differences. How many Kelvin? How many degrees Celsius? Yes, we can say, oh, that's cold, or we could say, oh, it's at 40 degrees, but 40 degrees does not mean that it has a certain amount of Kelvin. This is important that you separate these two ideas and that we work very diligently on understanding when we are talking about heat, when we are describing heat using temperature, and when we are going to calculate heat using our standard unit of joules. Now we get to talk about two prefixes that are going to be used greatly in this chapter to help us describe where energy is going. An exothermic process is any process that gives off heat. This means that we are going to transfer thermal energy from our system into the universe or our surroundings. So if you'll see this reaction, I have two hydrogen gases plus O2 gas going to form a amount of liquid water, 2 moles, and you will see that I form energy. If energy is seen in the products, this means that this is going to be an exothermic process. So now you can see that if I'm going to take my water vapor, as you can see here with H2O gas, and convert it to a liquid, we look at that as cooling it down. But what is actually happening is that as we are cooling that down, our water is losing energy. That energy is going into the surroundings, and that is how we get condensation and us forming a liquid. An endothermic process is the opposite of what we see with our exo. This is where heat has to be supplied to the system from the surroundings. So energy must be coming in order for this process to work. So now you can see here, if I would like to convert my mercury oxide to mercury liquid and O2 gas, I need to input energy in order for this reaction to occur. Our endothermic reactions are just as important in chemistry as exothermic, and while they may not happen as often, we are going to use many exothermic reactions to feed energy in to our endothermic processes. As you can see here, if I'd like to melt ice cubes, you are used to saying, I'm just going to heat it up. Well, then you would say, I'm going to raise the temperature. What you're actually doing is giving that ice cube energy to weaken its intermolecular forces, and that is what is going and causing our phase change. So in the case of an endothermic process, you are wanting to hope that our energy is on the reactant side. Now, for most balanced chemical equations, you will not have the energy put in blatantly on the side of whether it's the reactants or the products, and we will come up with a notation set of putting it off to the side with a plus or minus sign later in this chapter to make your lives much easier and have a standard notation set. Another way that we can look at this is using energy level diagrams. This is a nice way to describe visually how systems either gain or lose energy. So let's go ahead and look at the first one here on the left. You will see that my reactants are going to go to the products by the direction the arrow is going. So you'll notice that the arrow always goes from reactants to products. In this case, our reactants are higher in energy, going and forming lower energy products. Well, where does that energy go? This means that it must be given off to the surroundings, and our left diagram is an exothermic reaction. So if your reactants are higher up on your energy level diagram, and then our products are farther down, this is going to be an exothermic reaction, and you will see downward facing arrows. As you can see in our endothermic example here on the right, we are actually going and taking a stable reactant, our HGO, and you'll notice that I will go once again from my reactants towards the products, but now I will have formed more unstable products. Well, how do I do that? I must add energy in. So as you can see here, if I have an arrow going up, I need to give my reactants energy in order to have more unstable products. This is the visual way of describing an endothermic reaction. Let's take a look and see if you can understand some of the important theory that we've discussed so far in this video. When dealing with the concepts of thermodynamics, which of the following statements are true? Number one, upward pointing arrows on energy diagrams are associated with endothermic reactions. Well, this is a true statement. The reason why is that if we have upward pointing arrows, we need to add energy in. So remember, if you see an upward pointing arrow, we are going to add energy. If we have downward pointing arrows, we are going to lose energy because our products are going to become more stable. So let's go ahead and look at number 2. Heat absorbed from the surroundings is considered exothermic. That is not correct. Remember, if our surroundings are gaining our heat, then that would be exothermic. But in this case, heat being absorbed from the surroundings means that energy is coming in. So if we wanted this to be correct, we would have to call this an endothermic process. So our second possible answer is not correct. So let's look at 3. Conduction is the transfer of energy through electromagnetic radiation. That is not correct. Remember that conduction is through the motion of molecules. If we want to talk about electromagnetic radiation, well, that is not conduction, and this would have to be radiation. So number 3 is not a correct answer. Finally, thermal energy is the energy associated with the sun. Now, while thermal energy is incredibly important, and we have seen that it's important so far in this video, this is not a correct answer. This is actually going to be radiant energy by definition. So our radiant energy is going to be the energy associated with the sun. So if we look at our answers here, the only correct answer that we see is going to be number 1, and so we will get letter A. It's really important that you work on understanding the basic definitions of thermodynamics, because as we build going through this chapter, we are going to use these fundamentals greatly. So now let's go back and talk about the first law of thermodynamics in its entirety. As we've already said, energy can be converted from one form to another, but it cannot be created or destroyed. This is important because now we are going to deal with internal energy. This means that delta U, our internal energy of the system and the surroundings, the entire universe together, must be equal to 0. So a better way of explaining this is that the internal energy of our system, whatever we gain or lose, the surroundings must have the immediately opposite sign because it is going to do the reverse reaction. If our system were to gain energy, our surroundings have to inevitably lose that energy, and vice versa. This is probably the easiest mathematical explanation of how our internal energy works in a system. So as you can see here, I am going to go and burn propane. I am going to take my propane, mix it with oxygen, and form CO2 and water. This is an exothermic chemical reaction. So what does that mean? That my chemical energy lost by the combustion, the breaking of my carbon-hydrogen bonds, and the formation of my carbon dioxide and water, which we saw previously in bond enthalpy, all of that energy that was released now is going to be gained by our surroundings. This is really beneficial for us when we're cooking food on a grill, because if we burn propane, all of that energy is then absorbed by our meat, which then cooks it so it is safe for consumption. So I want you to always look at any energy transfer as who is losing the energy and what part is gaining that energy. If you understand that directionality, you are going to be able to solve many of the difficult math concepts that we will see throughout this chapter. So there's another form of the first law of thermodynamics, and that is now combining two types of energy to describe our internal energy. So our delta U is the change in internal energy of a system. This means we are going to take stock in most of the energy types all at once. The two energy types that we are going to sum in order to help calculate that is Q. And the first one of that is the heat exchange between the system and the surroundings. So Q is going to be our heat. Our W is going to be work done on or by the system. As we will show you here in a moment, the sign convention for these problems is incredibly important. Another way we can calculate work is talk about a gas expansion. That is saying that work is equal to negative P times our change in volume. We are going to do example problems with that math in the next video. So now let's take a look at our bottom chart here to help you understand the sign convention for our heat and our work. So if we have work done by the system on the surroundings, this is going to get a negative sign. So as we look at our W equals negative P delta V, if we have work done by the system on the surroundings, historically, we are going to call that an expansion. So in this case, in an expansion, our volume is going to get bigger. So this means that we are going to get a positive delta V. Well, as you can see in our equation, if I have a positive delta V times a negative P, that is how we end up with the negative sign that we are going to commonly associate with work done by the system. Say we flip that and it's now the surroundings who are doing the work on our system. We will typically call that a compression. A compression means that we are going to take our volume and make it smaller. So now what happens is that our delta V is going to get negative. This means that it's going to make our gas sample smaller. Two negatives make a positive, and that is how we result with the positive that you see here. When heat is absorbed by the system from the surroundings, this is an endothermic process. From this point forward, endothermic processes are going to be labeled as positives for our Qs. When dealing with heat absorbed by the surroundings from the system, that means that we are releasing energy from our system into the surroundings. That is an exothermic process. That is energy being released. And as you can see, we are going to use a negative sign. So now what we're going to do is do a few examples to look at this math, and it is going to be the most difficult, easy math that we probably do in this chapter. So let's look at example 10.2. The work done when a gas expands in a cylinder is 285 joules. During this process, there is a heat transfer of 128 joules from the gas to the surroundings. Calculate the energy change for this process. So what we are able to do is say that we have delta U equals Q plus W. So now what we need to do is go and look at the sign of the two numbers that we have. So let's go ahead and first deal with work. It says that our gas expands. Remember that when gas expands, that is a positive delta V, which means that we are going to get a negative W. So in this case, for our 285 joules, our work in this case is going to be minus 285 joules. That is how I get the negative value. So now let's go ahead and take a look at our heat. It says that there is a heat transfer of 128 joules from the gas to the surroundings. So what does that mean? Well, from the gas means that we are going to have an exothermic process. Exothermic releases energy into the surroundings. So this means that our value must be negative as well. So that is going to give us a negative Q, and our Q can be expected to be negative 128 joules. So what can I do? Well, now what I can do is put those into my equation. So I have my Q at negative 128 joules. We are going to subtract because we have a negative 285, or we can go and add a negative 285 joules. And now you can see why I will call this the hardest, easiest math you'll do. The hard part is trying to determine the sign. But now that you have these values, all you need to do is put them in your calculator, and you're able to determine that negative 413 joules of internal energy were released throughout this process. So remember, the negative is going to say that that energy is being released. Let's go ahead and try a second example of this. This comes from the fall of 2016 exam. A system conducts 255 joules of heat to the surroundings while having 428 joules of work being done on it. What is the change in internal energy of the system in joules? So now we are going to go back and use our first law of thermodynamics equation. So now we have our Q plus W. So now we need to work with our Q first. So which one is going to be our Q? Well, you can see right here it says 255 joules of heat. And you'll also see that it is going to go to the surroundings. This means that we are going to have an exothermic process. So is that positive or negative? Remember, exothermic means that it is negative. So we have negative 255 joules. So now let us go ahead and look at the work. And it says that it is 428 joules of work being done on it. This means that the surroundings are doing work on the system. So this means that we are going to deal with a compression. So this also means that we are going to have a smaller volume, and we are going to end up with positive work. So we can say that our second term would be a positive 428 joules. And if I do this math, you will see that I will need 173 joules of internal energy put into this system in order for this to be accomplished. If I look at my answers on the left, you will see that I get answer A. Now we can go ahead and look at work being done by the system on the surroundings. So now you can see that work is actually force times distance, which gives us the joule. This is a very physics definition. We can also say that work is equal to negative P delta V, and you will see that we are going to get the units of the liter atmosphere. This is going to be important because in the next video, I will show you how to convert from the liter atmosphere to our joules. So now what is neat about this reaction is that we are able to go and show you exactly what we mean by a compression or an expansion. So as you see here with my initial volume, if I expand, notice that I am fighting against an external pressure, which means that I'm going to need to have some form of energy for our change in volume. In this case, we cannot just go and describe this as the change of final minus initial. The reason why we cannot do this for work is that work is not a state function. So what is a state function? Well, a state function are properties that are determined by the state of the system regardless of how we get there. State functions include energy. So let's take a look at these two hikers. We can all agree that they are at the same ending point. But the interesting part is that if we look at this in the terms of potential energy, they have the same potential energy difference from where they started and began, but let's see who worked harder. If we think about work not being a state function, can't we agree that the blue line worked less on a time thing, but you'll notice that they have worked harder by going up the higher end of the cliff. Our red line will have worked longer, but he has gone a much easier path in which he is not scaling up the side of the mountain. This should be a visual representation on why work is not a state function, but you can see that our potential energy is. So the nice part about this is that we can start to build a set of equations that is going to help us. So in the case of our internal energy, final minus initial works wonderfully, and we are able to do this calculation. If we were to do the same for pressure, volume, and temperature, which are also state functions, you will see that I am able to go and do the same calculation. A state function, when noticed, is an important assumption for us when we are doing calculations, because if you see state function, we don't care how we get there. All we want is final minus initial. This is going to be incredibly beneficial for you as we are going and doing some of the calculations, not only in Chem 119, but also in 120. In this video, you saw the importance of not only the fundamental definitions of our thermodynamics, especially when describing our system and surroundings and the direction of our energy change, but then we also saw the importance of the first law of thermodynamics and how we can describe how energy is leaving or coming in, and then finally what a state function is. How can we describe a state function, and do we need to calculate its path? In the next video, you're going to see some of the important calculations that are going to be used using this fundamentals. Have a great day.